So I'll be talking about a polynomial time algorithm to solve the bounded distance decoding problem, but for a specific class of lattices. Now, the closest vector problem in general, even if you fix the family of lattices, can be NP-hard. So getting polynomial time algorithms is something that can be done only for specific families. I will not solve the closest vector problem. I will solve a special version. So remember, in the closest vector problem, should I use the black color or green is okay? Black is better? Yeah. Oh, yeah, here. So let's say you are given, so the closest vector problem, in general, you are given a lattice L, and which you may assume to be an integer lattice, if you like, and you are given a target point T, and the goal is to find the lattice point V in L such that the distance to the target is minimized. Now, a special version of this problem, which is relevant in cryptography, communication theory, and many other applications, is solve this problem when the solution is guaranteed to be unique. More specifically, so this is called bounded distance decoding, which is CVP when the distance of T to the closest lattice vector is guaranteed to be less than half the minimum distance of the lattice. Notice this guarantees uniqueness of the solution because geometrically, if you have a lattice, so the minimum distance is the distance between two nearby lattice points. So if you put spheres around the lattice points, when the radius of the sphere becomes half the minimum distance, two spheres are going to intersect. So if I give you a point in the intersection of the two spheres, the closest point could be either one or the other one. But as long as the distance to the lattice is less than lambda 1 over 2, then the solution is unique because the spheres are disjoint. So this is the problem that I'm going to solve efficiently. And I'm going to do that for a specific family of lattices called Barnes wall lattices. And the algorithm I'm going to present is joint work with Antonio Nicolosi. So this family of lattices is most easily described as a lattice over the Gaussian integers. So using complex numbers rather than just the plain integers. It really makes everything nicer to describe. So I'll do that. But before we do that, maybe I'll give a brief explanation of how that works. It's pretty obvious. It's what you can imagine. So we take the set G of Gaussian integers, that is the sum of z plus iz, where z is the imaginary unit. And so you can think of the elements of G as two-dimensional integer vectors. So this is just the same as z square, where the complex number a plus ib is identified with a two-dimensional vector ab. So, so I'm going to give a complex basis for the lattice. The lattice is going to be described by a basis. I'm going to give a basis which is a matrix with complex entries, and the lattice defined by this basis is precisely the set of complex vectors of the form Bx, where x is an integer, Gaussian integer set of coefficients. And you can think of this as a n-dimensional lattice with complex entries, or equivalently, you can turn each complex entry into a two-dimensional integer vector, and that will give you an integer vector with 2n components. And so how do you get it? What if you want a basis over the integers? Notice if you take, so let's define this map. Let's give a name. So let's call it phi. Is the map from the complex integers to two-dimensional to this to Z2. And this map is applied to vectors component-wise, going from dimension n to dimension 2n. And so if I give you a basis, let's consider the simplest case. You have a one-dimensional lattice. You have A plus IB. And consider the lattice generated by alpha. So the lattice generated by alpha is alpha times G. And we want to look at this lattice as an integer lattice. So for every, so the multiplication of complex numbers can also be expressed as you can. There is a ring isomorphism between the complex numbers and 2 by 2 matrices. You can represent a complex number alpha as the matrix A, B minus B, A. And you can easily check that matrix multiplication for these matrices is commutative. It corresponds exactly to the multiplication of complex numbers. And if you take this number alpha and you multiply it by G, what you get is exactly the lattice generated by the matrix M alpha, which in this case is multiplied by Z square. Okay? So if I give you an n by n matrix with integer entries, you can apply this function M to your basis B component-wise, and you get a matrix with integer entries, which is 2n by 2n. You just expand every complex number into a 2 by 2 matrix, and then instead of multiplying it by Gaussian integers, you multiply them by regular integers. Okay? So one nice thing to observe is that the norm of a vector is just the same as if you use complex numbers. So the norm of alpha of A plus IB, if you take the norm squared as a complex number, that's A squared plus B squared. That's exactly the same as the norm square of the corresponding vector, of the square norm of the corresponding vector. A square plus B square. So we can freely use complex numbers and do the operations on them. Of course, I mean, addition is addition, and norm is norm, and everything works fine. Is everybody happy with complex numbers? Okay. I'm not using complex numbers to make this look more complex and ingenious than it actually is. It actually makes things simpler to define. More specifically, using complex numbers, using Gaussian integers, there is a very, very simple definition of these Barnes-Wall lattices. So these are an infinite family of lattices. In complexity theory, if you fix the dimension, all lattice problems can be solved in polynomial time using LLL plus exhaustive search or some other algorithm. So in order to work with asymptotically, with hard problems, we need to consider family of lattices in larger and larger dimension. So Barnes wall lattices is one of the most prominent families, infinite families of lattices in larger and larger dimensions. And it is defined only for dimensions which are a power of 2. And I'm going to define these lattices for complex dimension that is a power of 2. So this is going to be a matrix, an n by n matrix with complex entries, which equivalently you can write as a basis in dimension 2n times 2n using that transformation. But expressing it, defining it without using, it is harder to define it using integers. So using complex numbers, there is a very...
Isomorphic, you just get a subring. Not every matrix looks like that.
Sure, of course. Not every matrix, but So this embedding, So this, yes. I'm not saying that. So the lattices that they generate are isomorphic. So the lattice generated by Bn is a subset of G to the n, which is isomorphic as Z to the 2n. And no, as matrices, no, because when I define it as a matrix over the complex numbers, I'm not only taking the integer linear combinations of the columns, I'm taking Gaussian integer combinations of the columns. Okay, so they are not isomorphic as just as groups, as modules over the integers. Okay, so in the case k equal to 0, no, let's take k equal to 1. K equal to 0 is probably just, all the integer vectors. But in the simplest case, I define this as the two-dimensional lattice generated by the 1 vector that has 1 in both components. So this one basis vector. And the other basis vector is 0, 1 plus I. Okay. In general, B for 2 to the k is the product of the tensor or Kronecker product of this matrix with itself k times, where the product of two matrices is defined, this is equivalent to the tensor. If you think of them as lattices, we are taking the tensor, or modules, we are taking the tensor product as modules. And there is a simple operation to describe this operation on the basis. On the basis, when you take, if you have two matrices, A and B, the product of A and B is obtained by replacing each element of A with an entire block which is a copy of B. This would be 1n or n1. n1 times B. In particular, if A is an n by n matrix, and B is a H by H matrix, then the product is an NH times NH matrix. The dimension of the space and the dimension of the matrices get multiplied. So this is the definition of the lattice. So, okay, what kind of lattice is this? And why is it good? And let's get some sense of the geometry of the lattice. Now it's hard to visualize things in n-dimensional space. So let's just look at some one-dimensional quantity associated to this lattice. So one way to, let's see how it compares to Zn, to the set of all integer vectors. Or to n, if we wanted to match the dimension there. Now, so this Z to n is a very special lattice. It's a lattice that has an orthogonal basis. It has n vectors of length 1, which are all orthogonal to each other. And in particular, the minimum distance of the lattice is equal to 1, and the determinant of the lattice is equal also to 1. This is the set of all integer vectors. The determinant is 1. Now, when comparing the two different lattices, of course, you can increase the minimum distance by scaling the lattice. So in order to make a fair comparison, you can compare them when normalizing them so that the determinant is 1. So, so let's take this lattice, this Barnes-Wall lattice. Let's look at what is the determinant of the lattice. Let's look at what is the minimum distance of the lattice, and let's see how it compares to the integers. And it's easy to see that it's a much, much denser lattice than Zn. Now, how do we compare? So I will, it's fairly easy to compute both the determinant and the minimum distance of these lattices. In particular, the determinant of the Barnes-Wall lattice, the determinant gets multiplied when you take tensor products. So the determinant of the Barnes-Wall lattice, so this is just a diagonal matrix, so you get 1 plus I to the power little k. And here we are taking the square, the modulus. Is this correct that it gets squared? So let's just check. So if we just take B3. So in B3, also as an example of how we combine these two matrices. Before, yeah, 3, k equal 3. So, so if you take 1, 1, 0, let's give a name to this prime, to 1 plus I. How shall we call it? J? Does it have, does it have a standard name? That's the smallest prime in G, so it's so sure it has a name. Okay, let's call it J. And if you multiply it with itself, you get a 4 by 4 matrix, which on the diagonal is 1 J, J, J square. And here we have 0. So the matrix is still triangular. And if you want to write all of it, here you have a copy of 1, 0, J. So the determinant is J to the 4. So it's not. Okay, so you can compute so that's not the value, but you can compute it. So you can compute explicitly what are you can compute just the product of the diagonal elements. And you can express then the determinant recursively. So the determinant in dimension n is equal to the determinant in dimension n over 2 which comes from the first diagonal block times the determinant of this matrix, which is obtained by multiplying this by J. So we get J to the power n over 2, or maybe n because we go from integer or Gaussian integer, I'm not sure. I know what the final answer is, so I can just, okay. So,
Square
and this one gets squared because we have it again. So is this j to the n over 2? Hmm? No, there is an exponent because this one is not just a scalar matrix. So we are multiplying by j all of its coordinates. So we have j, n over 2, should be n over 2, correct? Yeah. Yes, and of course we are taking this is the absolute value of j. So let's see if it works, if this is correct for the for 4. If it's correct for 4, sure it's correct for everything. So we get j square times j 4 over 2 square, j to the power 4, which is the correct value. So by induction, we got it right. So you can compute it for every, I mean, this is the inductive formula to compute the determinant, and it is right. So you can unfold everything, and you will get the determinant of the lattice is precisely square root of n to the power n. And okay, prove it by induction. So that well, once you know the result, you can just check that by induction it is correct.
That is the determinant of the z lattice, while the one below is of the zi lattice.
Yeah, is it over Bn or is it over Z? That is,
Yeah.
that makes a difference.
It should be the same.
It's 2 to the 4th and not j to the 4th.
Yeah, right. So you have to take the
You
norm.
have to take the norm.
I have to take the what?
The norm of the formula for the determinant of B4 is the zi determinant. That you have. So the bottom line is the zi determinant
This
of B4. And now to get the z determinant, you take the norm. So you get 2 to the 4th. I think.
Well, no, that's
No.
not equal. That is square root.
Implies.
So your formulas are not consistent with each other because G to the 4 is 4 to the 4 the square root.
So if we square, if we put an exponent 2 somewhere, does it get closer to right?
It makes it only worse. It makes it worse.
If you divide it by 2?
Yes. No, but there is a difference between the determinant viewed as a matrix over Zi and the bigger thing over Z.
But they should be related.
Yeah, right. The thing over Z is the norm from the thing over Zi. So just
Oh, just take the norm. Okay.
That's the value squared.
So this one is the norm of this determinant.
Yeah, squared.
And so we take the square root of? No.
So it's
Square.
the square, right?
There. And this one, of course, has to be to the 4th.
And then
And we remove. Oh, yeah, I had the feeling that this over 2 needed to be replaced. So we need to replace, yeah, take the, yes, okay.
this looks right.
Okay? Now, the only reason I'm using the complex number, Gaussian integers, is because I can define the lattice easily, okay? Now, try to define it, but without just using the integer. And this one is not a scalar anymore. Then you need to put some matrices, and it gets a bit nasty not nasty, it's just almost as easy, but not as convenient notationally. So I want to use this notation to specify the lattices, but I want to think of them as lattices over Z. So think of them as lattices over Z, determinant is over Z, everything is over Z, and I will use complex numbers as a compact notation for these integer vectors. So the question number 2 is, what is the minimum distance of this lattice? And so there's something nice. So if you take this basis matrix, all the vectors have the same norm, and those are all the successive minima of the lattice. So lambda 1 is equal to lambda n, just as for Z. And they are all equal to the length of these vectors, which is exactly square root of n. For the first one, it is clear. You have the all one vector in dimension n. So these are one complex. So when you map them to the integers, this is the vector 1, 0, 1, 0, 1, 0. Okay? So there are only n, big N, ones, and the length of the vector is n. And so why is that true? Why these are the shortest vectors in this lattice? There is a simple way to see it. Now, if you don't use, so think of writing your vector using this tensorial decomposition. Now, if you don't use this part, your vector will be a vector repeated twice. So the minimum distance in this dimension will be square root of 2, for the whole lattice, will be square root of 2 times the minimum distance in the previous lattice in the sequence. So when you go from one dimension to the next, the length of these vectors goes up by a square root of 2 factor. That's also true if you take a vector of this form. The norm of 1 plus I is precisely square root of 2. So whether you use this or you use that, you get a square root of 2 factor. You can also take combinations. But it's easy to see that either you have a vector of the form 0 something, where something is multiplied by 1 plus I, or you have a vector where both the top part and bottom part are non-zero elements of Bn over 2. So Bn, the lattice generated by Bn, is always a subset. So the top part and bottom part are elements of Bn over 2. Not all of them. It's a strict inclusion. And that's just because this matrix it generates a sublattice of the identity matrix. So if you replace, if you write Bn as the lattice generated by 1, 1, 0, j times Bn over 2, the lattice is a subset of 1, 0, 0, 1 tensor Bn over 2, which is the set of all pairs of vectors, both coming from this lower dimensional lattice.
Yeah, and the last line should be Bn
over 2, yes. So this one property. The other one is that it's not all of it. In particular, if you want the first half to be 0, the second half goes up by a factor. So it is the intersection of this and the 0 as a set, 0 to the n over 2. Times j times Bn over 2. So all the vectors in this lattice can be divided into, so there are two kinds of vectors. Those that are non-zero both in the top half and bottom half, and each one of them has norm at least this much, and the new norm goes up by a factor square root of 2. Or they are 0 in the top part, non-zero in the bottom part, but then in the bottom part they cannot be arbitrary elements of Bn over 2. They must be multiples of j, and that also contributes square root of 2 to the norm.
But in the bottom it can be 0 and divisible by j in the top.
Yes, it is symmetric. So the lattice is, so there are, this lattice has a lot of symmetries. One of them is the one that swaps the top and bottom. I was using, yeah, top 0 and...
How can you intersect these?
Intersection is probably not the operation.
Yeah, maybe intersection is not, but so all, no, well, it is. It is a subset of the intersection.
No, but that makes the rank.
No, that's true. No, is the operation is the set of vectors where this is 0 are containing that. So it's not even the union. I mean, I can write, okay, so I don't know what the operation is, but I can define the set of, so the vectors, so all the vectors in this lattice satisfy the property that, so if uv is in Bn, then it follows that either u and v are non-zero elements of Bn over 2.
Both non-zero.
Both of them are non-zero.
Or they are both divisible by J.
Or if one of them is 0, yeah, sure, we can, or they are both divisible by J, and because one is 0, and yes. So if one of them is 0, the other one is a multiple of J, sure, then both of them are divisible by J. Yes, so yeah, we can write it or u is 0 and J and V is in J times Bn over 2.
Or the other way around.
Or the other way around. Which I think is redundant. I mean, these two are...
No, it's not redundant.
It's not? Okay.
Because you have to, yeah.
Yes. Yeah. Okay. So then, or V is 0, and U is J in J Bn over 2. Okay. But anyway, so this is just to compute these quantities. And what is more interesting is, so how does it compare with the integer lattice? So in order to make a fair comparison, let's normalize this lattice so that the determinant becomes 1. Or more generally, let's consider the quantity lambda 1 divided by the root of the determinant. So we take the determinant of the lattice, real integer lattice, and we take the nth root when n is the dimension, in our case is 2n. And for the integer lattice, this quantity is equal to 1. So the minimum distance of the lattice with normalized determinant is 1. So in this case, in the Barnes-Wall lattice, lambda 1 over determinant to the power 1 over 2n of the Barnes-Wall lattice in dimension n is square root of big N divided by square root of n to the n to the power the 2nth root. And n goes away, and you get the square root of n over 4th root of n, which is 4th root of n. So instead, over z. I'm using the complex numbers only for as a notation to represent the vectors. It's for everything else better to think of so I'm using I'm looking at the real quantities. So as a real lattice, the normalized length of the shortest vector so it is as dense as the integers. The determinant is 1. So on average, there is 1 lattice point for every unit of volume in space. But instead of being 1 apart, the lattice points, in terms of minimum distance, the minimum distance between any 2 points in this lattice is the 4th root of the dimension.
Is there also a formula for the number of shortest vectors?
Yes, there is a formula for the, yeah, that's called the kissing number of the Barnes-Wall lattice, and there is a formula for it. I don't have it handy, and it's some summation with a few binomial coefficients and powers of 2, and yeah, it's a relatively simple formula, but not as small as this, and unless I have it here, I don't think I can reproduce it on the fly. Yeah, no, I don't have it here. Okay. And there is also a formula, I believe, for the size of the automorphism group of this lattice. And again, it's something that involves summations with binomial coefficients, and I don't have, but it's big. So what we'll do is to look at some isomorphisms and use them to solve the bounded distance decoding problem. Now okay, I'll go back to the group of automorphisms at the end.
And this is not a root lattice over here.
It's not a root lattice. It's not a root lattice. Okay, so since you're asking, so what is the automorphism group? How can we connect it with some other areas of mathematics I don't know anything about? So from what I understand, the automorphism group of this lattice is the index 2 subgroup of the Clifford group. Okay? So if you know about Clifford algebra, if you know about Pauli matrices, quantum this and quantum that, then yes, you, okay.
So is there a relation to the Leech lattice?
Well, each lattice is only in dimension 24, which is not even a power of 2, so I wouldn't know how to relate the two. So the dimensions do not of the, yeah, so sure the Leech lattice is not one of them. I can tell you that for sure. Yes, I think that, so this, I think that it's in the Conway Sloan book, I think that this is called Lambda 16, yeah. So the book says, I mean, in the low dimension, they received even more attention. I think that Lambda 16, the 16-dimensional Barnes-Wall, is a sublattice of Leech lattice in dimension 24. So yes, you can find it. But I think that any lattice is a sublattice of the Leech lattice. I mean, any lattice in dimension you can find everything in there. So yeah, it's I have no intuition of how putting this lambda 16 inside the Leech lattice. But it is a laminated lattice in dimension 16. I don't know if it's true for every dimension, but yes, the reason maybe so, because I think they were using this notation lambda for laminated lattices. I don't know if it's true also for higher powers. Anyway, so I will use only basic elementary mathematics to show how to solve the bounded distance decoding for this lattice in polynomial time. Now, notice for root lattices, I believe that, so let me make some space first. So say AN and their duals, AN star. If you don't know what a root lattice is, it doesn't matter. It's just to answer the question, what about root lattices? So I think that so the root lattices, AN and their duals, are all special cases of Coxeter lattices. I hope I spelled it correctly. And all these lattices, I think they can all be decomposed into n cosets of Zn, or a scaled multiple of Zn. So a simple way to solve the not only BDD, even the closest vector problem in polynomial time, is to go through these n cosets and solve the closest vector problem in Zn, just rounding the coordinates. And that will solve the closest vector problem in all those lattices, and giving running time n square. And if you work on it, so there are some ingenious algorithms solving the closest vector problem in these lattices in time n instead of n squared. So you can solve it even fast, but solving the closest vector problem in these lattices in polynomial time is essentially as trivial as solving the closest vector problem in polynomial time in Zn, when you have a perfectly orthogonal basis. Now, just by determinant computation, if you ask the question, how can I express this lattice as a union of many copies of Zn, you can easily see that, you need an exponential number of copies of Zn before you can decompose this lattice into shifted copies and so on.
What do you mean by perfectly orthogonal?
Zn, a scaling of Zn, yes. You don't even need to rotate it, so you can, I mean, if you need to rotate it, then you can, and if you know enough automorphisms, then you can use the Gentry, Zidlo, and generalization algorithms and find the rotation, but you don't even need that. So anyway, so this one is an example of a highly non-trivial lattice where you may want to solve the closest vector problem. In fact, I don't know how to solve the closest vector problem. Solving the closest vector problem in this lattice is an open problem, and what I'll show you is only how to solve efficiently the bounded distance decoding problem. Okay? Now, don't worry, I already took quite a bit of time, but the algorithm is fairly simple, and also the reason it works, it is fairly simple. So, and the algorithm is based on the following 4 observations. Observation number 1, which I already wrote. If the vector z0, z1 belongs to the Barnes-Wall lattice of index, let me use the logarithm, the k, that instead of the 2 to the k. So in this lattice, in the k plus 1, then both the top and the bottom part of the vector belong to the Barnes-Wall lattice of index k. Okay, we have seen this already. So observation number 2, which is also pretty trivial. It's not even an observation, it's just a calculation. So what is the norm of z0, z1? It is the sum of the square norm of z0 plus the square norm of z1. In particular, so far, okay, completely trivial. What is the observation? That if the norm of this vector, so if you have a point in space which is within distance, if the distance between this vector z and the Barnes-Wall lattice is less than half the minimum distance, let's take the square. If the square distance to the lattice is less than the square of the half minimum distance, so if you are in the bound.
What is n here now? 2 to the k plus 1?
Yes. So yes, plus 1. No.
What is your capital N? Since over there it was 2 to the k, but now it seems to be 2 to the k plus 1.
Replace k plus 1 by k and k by k plus 1.
Well, I don't know.
Okay, hold on a second.
So n is half the dimension, I suppose.
Yeah, I guess I should put a plus 1.
The complex matrix is k plus 1.
So n is 2 to the k plus 1.
Yes, okay. And so if we are in the bounded distance decoding setting, since the square, so if you take the square distance of the top part and the bottom part, and each one of them belongs to the lower dimensional Barnes wall lattice, so you know that either the distance of S0 to BWK is less than
What is S0?
no, Z, sorry. Half of that. Okay. It's, yes, I'm splitting the square distance, half here and half there. I'm saying all I want to say is that at least one of them has to be half the squared distance. So this one, we can also write it as n big N over 4. And if this is true, either this distance is less than okay, so let's, I'm getting, I think that I lost track of whether.
Distance square and one of them has to
Okay.
also be that.
So if n is, I think that here in the notes I have n equal to 2 to the k as over there. So here let's write 2n, okay? So big N is 2 to the k, so this one is over 2. And here we have
the square distance.
hmm?
The square distance.
The square distance, yes. So if the distance, square distance, is at most n over 2, then either z0 is at square distance n over 4, or z1 is at square distance less than n over 4. Because if both of them are bigger than n over 4, when you add them up, you get more than n over 2. Okay? And notice, this is exactly the bounded distance decoding radius for the lower dimensional lattice. So if you make to recursive call, the algorithm is recursive. If I give a target and I tell you, find the lattice point closest to it, you run the algorithm on the top half, you run the algorithm on the bottom half, and you know that for at least one of them, you will get a correct result. Typically, not both of them, and you don't know which one of them is correct. But you will be able to get the closest point to at least one of the two. Okay? And now enter the automorphism. Observation number 3. The function t that sends the vector z0, z1 to j over 2 z0 minus z1 z0 plus z1 is an automorphism of the Barnes wall lattice. And that's very easy to see because this is operating, is a block transformation operating on the top block and bottom block. You just need to check that it holds for the 2 by 2 matrix. Well, I'm using subscript and superscript inconsistently, but I will use only one of them. So it doesn't matter where I put the index. Okay? So, so this can be easily checked and is also related. So there are other, it's not the only one. There are many others, and you can If you take the powers of this automorphism, I think you get, for example, the squaring one, the swapping top and bottom. I think it's just the square of t, swapping the top part and the bottom part. But we are not going to use that. But yeah. And of course, other automorphisms are given by applying an automorphism at the bottom, and you take an automorphism of the lower dimensional lattice and apply it in parallel both to the first and second part of the vector. That also is going to give you an automorphism of the entire lattice. Because if you look at its basis, it's changing this vector with a vector that is 0 here and a multiple of j here, and this vector is sent to itself. Okay? So the algorithm is recursive, so in some sense it uses all of these automorphisms. I'm going to use only the top level one and then recurse, make a recursive call to the sublattices. And there is one last observation that we need to make. And from the 4 observations, you immediately get an algorithm. You can design an algorithm on your own. And the algorithm is the following. The two vectors, z0 and z1, can be recovered from any of the following pairs. So let's define z plus and z minus to be the result of this automorphism. Z plus and z minus. So if I give you z0 and z plus, then just using linear algebra, you can recover z0 and z1. They are related by an invertible linear transformation. If instead I give you z0 and z minus, again, you can recover z0 and z1, z0 is given to you. You can also recover z1 combining those two together. And the same is also true for z1, z plus, and for z1, z minus. And I don't know what is the most elegant way to conclude that you can recover that from any of those 4 pairs, but I know what is the fastest way, which is just solve the 4 linear system. And for example, you can compute z0 as Okay, so let's just jump to the algorithm. So when you run the algorithm, so the algorithm works by taking a target vector, say t0 and t1, and it does the following. It defines t plus and t minus by applying the automorphism to the target. And then it applies recursively the algorithm on all of these 4 values. And you get z0, z1, z plus, and z minus. And you know that at least one of these 2 is correct, and at least one of these 2 is correct, and you don't know which one is correct. Fine, just consider the 4 possibilities, and for each of these 4 possibilities, recover the correct value just using linear algebra. So one possibility, if the correct values are 0 and minus, then you can recover the closest vector as the vector, well, z0, you leave it as it is, and the other vector you set it as to z0 minus 2j minus 1 z minus. And you can check that this is correct. And similarly, you can set z0 plus to z0, but this time you don't have z minus, or better, the values of z minus that you got, maybe it's wrong. If z minus is wrong, then you know that z plus is correct, and then you can compute the bottom part as 2j minus 1 z plus minus z0. And similarly for z1 plus and z1 minus. So you compute these 4 candidate solutions, and you pick the one that is closest to the target. You know that one of them is the unique closest lattice vector. So if you pick the closest, even without knowing which recursive call worked, you will get the correct solution.
So how do you test which one is correct? Are they all in the lattice already? Or do you
Yeah, they are all in the lattice because they are, you can show that, so these are all in the lattice. No, not all. If the results are correct, then they are in the lattice.
Right.
Yes.
If they're not in the lattice, you could discard them.
Yeah, but you don't check membership in the lattice. It is easier just to check the distance to the target. Because you know that the...
You need to check that the thing you're given is a lattice vector. I mean, it could give you the target as an answer.
Oh, yeah, sure. Yeah. You check that they belong to the lattice. Yeah, you need to check that. Yeah, you check that they belong to the lattice, and then you select the closest point to the target.
Is the closest.
Because we are in the bounded distance decoding. You know that there is a unique correct solution, so that, yes, that works. So this is a very simple way of using an automorphism to design a decoding algorithm for a non-trivial lattice. And so all this is already written down. The paper is in International Symposium on Information Theory, 2008. And so, if you can double check everything. So,
the problem that makes unusable for the closest vector problem is that you wouldn't be able to choose in these, like when you go in depth. So you wouldn't be able to choose which one is correct, so you would get some kind of...
So if you want to solve the closest vector problem, the issue is that you could get inconsistent solutions. So you are getting 2 pieces of a solution. Let's say that there are 2 good solutions. And so when you, so you are making calls to lower dimension to get partial information about the solution. If you get partial information A about solution 1 and partial information B about solution 2, when you combine these 2 pieces of partial information, they are not consistent. So you cannot just use linear algebra to reconstruct. However, something can be said. So you can go beyond the bounded distance decoding radius by, so you can compute the least decoding radius of this lattice, which is, you can show that as long as the distance is at most twice as much, there is only a polynomial number of solutions. So you can compute, you can try to compute all of them. So Chris Pikert and Elena Grigorescu showed that this same algorithm, if instead of getting a solution from every recursive call, you get a list of solutions, and then you combine these solutions in all these 4 possible ways, and then you discard the solutions that are too long, far away from the target, they show that up to the least decoding radius, the size of the list stays polynomial. So you can go beyond the unique decoding radius to twice as much by using lists of solution. Going beyond that, so if you go beyond that, the number of solutions can be exponentially large. You can still define the closest vector problem as producing any of them. You know, it's I don't want all of their algorithm gives all the solutions within that radius. So you can define the closest vector problem as producing any lattice point which is closest to the target. If there are exponentially many of them, just give me one. And that we don't know how to do it. But there is potential of using the automorphism group of the lattice to go. In fact, I mean, I'm trying to do that. The problem is that I'm stuck at understanding these Clifford algebras, which are exactly what comes up when you look at the automorphism group. But yeah. So more interestingly, you see how even with just one automorphism, it is possible to do highly non-trivial things. And there are many other structured lattices coming from algebraic number theory and related areas that I expect have a rich group of automorphisms. One family of lattices which I think is very interesting, but is just too much for computer scientists to study, is the family of lattices called Mordell-Weil lattices, which come from algebraic curves over function fields. Did I say it right? Yes. And so those are the lattices, and they are even denser than Barnes wall. In fact, they are much, much denser than Barnes wall. So one way to look at the density of these lattices is to take the, well, you know Voronoi cells, okay? So take the Voronoi cell of the lattice. In the case of Zn, the Voronoi cell is a cube. And if you put, let's look at how close is the Voronoi cell to a sphere. And you can define this as the ratio between a sphere, a ball inside the Voronoi cell, and a ball outside the Voronoi cell. And look at the ratio between these two spheres. So if the ratio is 1, then you square the circle. And yeah, you cannot get 1. So in the case of Zn, you get... In dimension 1, yes. Also in dimension 0, yes. And by induction in any dimension. So in the case of Zn, the ratio between these two radii is square root of n. In the case of the Barnes wall lattice, if I remember correctly, it's not an hexagon. I'm just drawing the hexagon for illustration purposes. And the ratio between these two quantities is somewhere in between the 4th root of n and the cubic root of n. And I believe that the exact value is not known, because the covering radius is not known. You can prove upper bounds on the covering radius just looking at the diagonal elements of the basis, and that gives an upper bound. You can compute lower bounds on the covering radius just looking at the determinant and the volume of the sphere, volume of the Voronoi cell. Of course, the volume of the sphere has to be smaller than the determinant of the lattice, and the volume of the other sphere is bigger than the determinant. But I believe that the exact value of this covering radius is not known. I think that Mordell-Weil lattices achieve a constant radius, which is, at least for some families, so it's a big family of lattices. I think that some of them achieve constant radius. And this is maybe something that was shown not by Mordell-Weil, but shown by Elkis and one more person. Kumar? I don't know. So I'm, so they are very, very dense. Some other lattice that comes somewhere in between these two is the family of lattices called Craig, unrelated to Craig Gentry, Craig, sometimes also called difference lattices, which can be, they have a very nice simple, elementary algebraic description. You can describe them as it's a family of lattices with two parameters, m and n, and they can be described as the ideal generated by x minus 1 to the power, one of them is bigger, one of them is larger, so as well, n is smaller, so let's say n is smaller. So you can, is the ideal x minus 1 to the n inside x minus 1 to the m. And, okay, so let's take, so it is an ideal in the ring Zx modulo x to the, oh sorry, m to minus 1. So let's say it is a cyclic lattice in dimension m, and it is the lattice corresponding to the ideal x minus 1 to the power n.
So it is of codimension 1. The rank will be m minus 1 then. Since there's a GCD x minus 1 in the polynomial.
Yes, and we take only the lattice point. It's not we only take the points which are orthogonal to the all one vector. Yes.
They are all orthogonal.
Yes, yeah, we only take the vectors that are orthogonal to 1, 1, 1, 1, 1. And but for these lattices, the minimum distance is not known exactly. And when m is prime, there are good lower bounds on the minimum distance. And I ran some, just computation. We know how to compute the shortest vectors in low dimensions. And I've seen that even when it's prime and the dimension is 50 or below, you can easily find lattices where the minimum distance is even better than the best known lower bound. But if we know the lower bound, then we can ask, if we know the minimum distance, we can ask, oh, can you come up with a decoding algorithm up to half the minimum distance? Or shorter, if we don't know the minimum distance, we can ask to decode it up to half the best known lower bound on the minimum distance. So we can take a computational version of the decoding up to the best known minimum distance bound. So these are interesting family of lattices. There is very little known. In fact, before this Barnes-Wall algorithm to decode Barnes-Wall lattices, I think that the only lattices for which we knew how to solve BDD or CVP in polynomial time were these lattices that have trivial algorithms by decomposing them in union of cosets of Zn. So, yeah. Pick any lattice and is solving the closest vector problem or boundary distance decoding is an open problem, which probably brings us to the open problem session. Let's say since I didn't go over time. I started the open problem session. So these are two open problems coming up with the bounded distance decoding or closest vector problem algorithms that run in polynomial time and decode these lattices. And for Mordell-Weil, I'm pretty sure that there's no competition from computer scientists working on them. Yeah, this I cannot even put down the definition. So if you give me the implementation of the algorithm, I will run it. Yeah, I'll compile it and run it. Okay. Okay. So that's it.